Alright, chemistry. Excuse me. So let's do this. I am picking up where I think we left off, which was I asked y'all to do 1 through 6 at the bottom and 1 through 8 at the top of page 56. I'm going to go through the bottom first, just because it's closer to what we did when we left off, and then I'll talk about the top part afterwards. First question number 1, the heat content for the reactants. Did y'all just see that freak out a little bit? Don't know. The heat content of the reactants is this space here, so it's 80. The heat content for the products, well, that's this space here, so that'll be 160. And then the activated complex is the very top of the hill, that's here, that'll be 240. Hopefully that was straightforward enough. Again, that was like what we did last time, so now let's do calculations based on that. So activation energy for the forward reaction, that's from here to the top of the hill, so it's 240 minus 80, that'll be 160. The heat of reaction is between the reactants and the product, so 160 minus 80, well, that's 80. In the forward reaction, we're gaining reaction, well, that's endothermic. Right, that looked pretty much exactly like we did on the other page. Now this one, the letters were a little hard to read. This was A, this was B, I got C and D, E, and F. Right, so if I'm looking for A through F, what is the potential energy of the products? Well, that's kind of like the heat content of the products from down below. So that should have been letter E. Let me do it lowercase so it's more obvious. Activated complex, well, that's top of the hill. That's going to be letter C. Potential energy of just the reactants, that's going to be A. Activation energy. Now notice, in number 4, actually for most of the ones we just did, they did not specify forwards or reverse, so safe to assume they mean the forwards. Activation energy is from where we start to the top of the hill, that's B. The heat of reaction is between the products and the reactants, so that's F. And is it endo or exo? Well, it's endo, and the reason it's endo is it ends higher than it started. Right? Activation energy, this time they say reverse, which means I need to start here and go to the top of the hill. Well, that is letter D. Heat of reaction for the reverse is the products minus the reactants. Heat of reaction is still represented by letter F. And the reverse reaction, I know I didn't ask you to do it, but if you logic your way through it, if forwards was endo, reverse should be exo. Alright. Now, you'll still get a little more practice doing that, working through diagrams before the test next Friday. But what I want to do, you'll notice my pages are going to go, well, oh yeah, no, they're going to go a little out of order because I'm going to go from 57 down here to page 60, and I'm going to talk about this because we're going to do a lab on Monday, A-Day, whatever that turns out to be for you. There's going to be another video that will go up in the very near future that will talk about page 58 and page 59. I'll ask you to do some of these questions on page 59. I would like that before A-Day, so just in between your F-Day and your A-Day, please, check that out, watch that video, because on A-Day we're going to be doing a lab. Alright, so I'm just going to very quickly talk about this stuff here on page 57 with what a catalyst is. So a catalyst is something that you will add to a chemical reaction that will speed it up and make it go faster. It doesn't become a part of the reaction. It doesn't get used up. You're not producing it. It's just something that you can put in to make things go faster. Later, if you wanted to, you could remove it. It would go slower again. Right? This is like a crucial part. It speeds up the reaction rate. It occurs to me that my pen is a little big here. Catalyst speeds up the rate by reducing activation energy, which makes the hill easier to climb, right? So if if down here, this is the normal reaction, the solid line, right? If I add a catalyst, the hill gets much lower, right? So it reduces the activation energy and it provides an alternate reaction pathway. Right, so you think of it, instead of having to go up and over the hill, you can actually kind of tunnel through the hill. So that's why it makes it faster. It does not change, I want you to look, it does not change where we start. It does not change where we end. It only changes this section here. It only changes how much energy do you need to start the reaction. Right? Entropy, I want you to notice that entropy looks... One take. There we go. Entropy looks like enthalpy, right? Enthalpy has an H, it means heat. Entropy has an R, which in this case kind of stands for randomness, right? This bolded line applies to all science, applies to all things. Systems in nature undergo changes that decrease in energy. Again, remember, the universe is lazy. And an increase in something that we call entropy. Now, the disorder, chaos, randomness of a system is measured by a quantity that we call entropy. It's represented by S. Now, you don't need to worry about the S, but know that if things get messier, entropy goes up. If things get more neat and more tidy, entropy goes down. All right, so entropy means how messy is it, how disorganized is it. There are some things that you can do to increase entropy. So if I increase temperature, it makes things go faster, which means they will move more randomly, they will move, and they will be more scattered. Changing phases from solid to liquid to gas. Solids are most ordered. Liquids are a little more random, a little more chaotic, a little more disordered. Gases are very disordered. If the reactants are simpler in structure than the products, that is to say that if there are fewer reactants than products, typically, so if I start with one compound at the beginning and I have two compounds at the end, I start with one substance, I end up with two substances at the end. Decomposition reactions are typically an increase in entropy because it's a higher level of disorder. Right? More moles of gas. Remember, the coefficients in front. So if everything is a gas, you can add up the coefficients on one side, add up the coefficients on the other side. If the number goes up, entropy goes up. If the number goes down, entropy goes down. Right? Or if you place a substance in solution, so if you dissolve it in water, you make it aqueous. If I take a solid something and I dissolve it in water, it separates into pieces, it dissolves, so it will become more messy, more disordered, more entropy. Right? So very quickly, I'll look at these examples. If I look at example number 1, I see that I have a solid going to gases. That's an increase in entropy. Alternatively, this is a decomposition. And I said that would be an increase in entropy. For number 2, if I look, they're all gases, so it's not super helpful with the phases, but I have 2 reactants, and I only have 1 product. This is a synthesis, which means entropy is go down. I'm taking multiple things, I'm combining them into one thing, right? That's more organized. My organization before was 2, now I have only 1. Right? The last one is another phase change of solid to aqueous. This is taking a sugar cube, dissolving it in water. If you dissolve it, entropy goes up, it increases. Right? Big deal with entropy is kind of recognize if you change something, will it go up and down? Up or down, sorry. And recognize that systems in nature decrease in energy, increase in entropy. Right? There we go. All right. Now, this page, which is page 60, talks about heating and cooling curves. All right. Now, first, it's a little misleading because they're not actually curves. right? It is straight lines, but it shows changes in energy as we go through phase changes, right? Heating curves are what we call it if the temperature goes up. Cooling curves are what we call it if the temperature goes down, right? So your picture is not colored, sorry, but on the picture here, the red is for a heating curve, the blue is for a cooling curve. You know, typical hot and cold colors. Right? Nothing to fill in here, but I would like to kind of look at some stuff. Everything on a heating curve is endothermic. Everything on a cooling curve is exothermic. That should kind of make sense. If we're increasing the temperature, we're adding heat to something, it's absorbing heat. That's endo. If we're cooling something down, it's releasing heat. It's giving it away. That's exo. Right. This thing here, freezing and melting, they actually happen at the same temperature. We're going to do a lab on that in the very near future. All right. So just be ready. We're good. The big deal, or the two big deals, I guess, are like this bullet point and this bullet point. Right? During melting, which is here, and vaporization, which is here, PE increases and KE stays the same. And there's no temperature change during a phase change. Notice, look, the temperature, which is measured on the y-axis, remains the same on line B, remains the same on line D, so temperature doesn't change, but something has to change because we are continuously adding heat. So kinetic energy cannot change because temperature is average kinetic energy, but the potential energy is absolutely going to change. So on a heating curve, if I'm adding heat, potential energy will go up, kinetic energy will stay the same. On a cooling curve, if I'm removing heat, kinetic energy will stay the same, but potential energy will go down. All right. A, C, and E all have temperature changes, so kinetic energy is changing, but potential energy is staying the same. All right. We're going to kind of discuss more about this. I will also discuss the remainder of page 60, which has to do with a couple more equations with heat. They're very simple. They're very straightforward. It's all reference table work. It's really just, can you read the question? Again, goes back to rule number 1, reading is hard. We'll talk about those when we talk about the lab, because it will be related there. Now, y'all should check out and look for a video explaining pages 58 and 59. Right? I'm going to ask you to do something here with page 59. You will have to use table H. It will be very straightforward. All right? It will have to do with vapor pressure. It's a very specific thing. It's the only thing that's really not review. Most of the rest of this, review. Vapor pressure will be a little new, but it's simple enough. It's kind of self-explanatory. It's vapor pressure, pressure from vapor. But anyway, that's going to be a video that will go up in the very near future. So look for that. Finish 58, 59. Do those notes. Do the questions that I will ask you to do. And until next time, whether it's class or video, take care of yourselves, kids. Be good.